Hello everyone and welcome back to my data science channel. Today we are going to predict the prices of apartments in my city. My name is Joanna, I'm a senior data scientist, and this is a beginner-friendly tutorial on using linear regression in Python. So whether you are just starting off with data science or if you are already a data scientist who wants to transition from R or Excel to Python, I think this tutorial is going to be suitable for you. I want this tutorial to be as close to reality as possible, and for this purpose I'm not going to use some existing dataset which was curated and which is suitable for performing linear regression. There are tons of tutorials with such datasets already on YouTube and which are really high quality. What I want to do with this tutorial is show you the reality. So I've built my own data set by scraping the website of a real estate agency and gathering data that I considered would be important in order to predict the price of apartments. I want us to bump into problems, and I want that not everything works perfectly by the book, so we can have a real intuition how we could address those problems, how could we bypass them, and how could we build a good enough linear model in a real life scenario. So let's just start by importing some libraries that I've already listed here. So for data management, Pickle, Pandas, and NumPy, and then for training a linear regression model, I've chose the Stats Models API, which is going to give us a summary that we can interpret in a more statistical way. Then for model evaluation, we are going to use the mean squared error and the mean absolute error. And then for visualizations, I'm importing the classical packages Seaborn, PyPlot, and PyLab. Okay, so I'm going to start off with loading the data, which is stored in a Pickle file in the same directory as this notebook. And I'm also going to check if my data loaded correctly as expected in a Pandas data frame, and also which is the size of my data, how many rows and how many columns I have. And then we will start off from there. My dataset has 161 rows and 11 columns. The columns are the price in euros, so this is what we are trying to predict. Then potential predictors, but we are not sure if we are going to use them yet or not, are the number of rooms each apartment has, its size in square meters, the number of bathrooms, number of balconies, whether it has a pass-through room or not, whether the apartment needs renovation, it's finished and ready to move into it, or it's not finished. Then we have the height position, which is a variable that I've calculated by dividing the floor on which the apartment is to the maximum number of floors in the building. So if an apartment is at the highest floor, then this height position variable will be 1. If it's on ground floor, it will be 0, and then everything in between is just going to be some intermediary floor. And we also have the situation when the value is negative, and that might be, that the apartment is at the basement of the building. Then we have the neighborhood where the apartment is located and which might play an important role, but more than the neighborhood, probably the zone would be more relevant. And this zone variable I created by just dividing the neighborhoods into the central neighborhoods and the rest of them. And we also have the year in which the building was built. So this is our data set, and I explained the variables that belong to it. Now let's just see a little bit how these variables look like in terms of how the values are distributed. For this, we need to look at some histograms for the numerical variables, for the numerical continuous variables. Then we should look at some scatter plots if we want to check the correlation between every pair of variables, respectively the correlation between what's going to be our dependent variable, the price in euros, and the other independent variables or predictors. If you are not very familiar with the concept of variables, numerical, continuous, predictors, responses, I would highly suggest to check my videos on variables, and that will give you a very clear intuition about what we are talking about here. So in order to get all this information together in one go, I'm going to use the Seaborn pair plot data, and I'm just going to pass in as an argument my entire data frame this time. This is going to take a while to generate. Okay, so 20 seconds later we have our pairs plot, which can be thought of as a matrix with columns and rows, and then on each one of the rows we have our variables, and exactly the same variables on exactly the same positions are also represented on the columns. On the diagonal of the pairs plot, where we would have the intersection of each variable with itself, instead of just plotting the scatter plot, which would make no sense because it would be just a straight diagonal line, this plot displays a histogram. And in this histogram, this is a histogram of all the values of that particular variable. So we can get more intuition about how the values are distributed. And we can see that our response variable, or what we will try to predict, the price in euros, is follows a sort of normal skewed distribution. So the distribution is skewed to the right. It means that it has a tail here to the right of it, which indicates that there are some apartments which have abnormally high values, and this might affect our linear model. Then at the intersection of each variable with a different variable from itself, we have a scatter plot. Some of our variables are numerical but discrete, others are continuous, and we also have a Boolean variable or categorical variables. Rooms, or the number of rooms in a flat, is one example of a discrete, numerical discrete variable. We can see that we have apartments with 1 room, 2 rooms, 3 and 4 rooms. We have flats with 1 room that have high prices, the same prices that apartments with 2 rooms would have. So they are overlapping in this area here. Then we have the size of the apartment in square meters, which is a continuous numerical variable. And we can see a very clear indication that the price in euros on the first column is correlated with the size of the apartment. And this makes sense. So the larger, or the more square meters the apartment has, the higher will be its price. We also have the number of bathrooms, 1, 2 or 3, number of balconies. Linear regression has one assumption related to the independence of the predictors. This means that when we are choosing the variables that will explain our response variable, our price, we must ensure that the predictors are not correlated, are not strongly correlated with each other. One counterexample would be that the size of the apartment and the number of rooms would be correlated, because you could not put 4 rooms in a 30 square meter apartment. And so I'm going to look at the intersection of rooms with size, and I'm going to see that indeed there seems to be a linear correlation between these two variables. So when I'll build my linear model, I'll pay attention on how I'm going to treat this correlation, or if I'm going to decide if I'll exclude one of these two variables from the model. Okay, so let's understand exactly what we are trying to do with a linear regression. Assume that we have one simple case where we are interested in predicting the price in euros based on the size in square meters. So we only have one predictor and one response. On the x-axis we'll put the predictor, the size in square meters. On the y-axis we'll put the response, the price in euros. And now we are collecting information about 15 apartments, recording each time the size of the apartment and its price respectively. With a linear regression, what we are actually trying to do is estimate an equation that is going to explain our behavior between the size of the apartment and the price in euros best. And what does this best mean? It means that if I were to predict the price of an apartment based on its size, the difference between my prediction and the reality is going to be as small as possible. But of course I have 15 apartments, and then for some of them my prediction is going to be better, or I'm going to predict exactly the real price. And then for other apartments, I'm going to predict way off. The goal is to find that configuration of parameters that is going to perform best over all the data points. So when we are going to measure the residuals between each prediction and the true value, overall the sum of all those residuals is going to be minimized. And actually what ordinary least squares does is it looks at the sum of the squared residuals. So not just at the residuals themselves, but it squares them. So what a linear regression does is trying to fit a linear equation to some data. And a linear equation has two components. It has the data itself and the parameters, or what we are trying to estimate. The data, because linear regression belongs to the supervised learning paradigm, will consist of labels, which are our y's, and predictors, which are the x's. The parameters are the component that we are estimating in a linear regression. They are not known a priori, and they are going to be different with each data set that we have. The configuration of parameters, or the set of parameters, is chosen based on minimizing this cost function, which in linear regression is the sum of squared residuals. If you were to think very hands-on and brainstorm on which are the factors that would impact the price of apartments, we could come up with a list, like I came up during scraping, like the size in square meters of an apartment, the floor on which it is located, the neighborhood, and so on. But there will also be some variation in the price in our data that probably we won't capture with these variables. Because there is also, for example, how big is the bid and the ask on the market, or what's the development trend of the city that we are looking at. And all these variables that we are not accounting for in our model are encoded in this epsilon, which are just the residuals, like the things that we are not counting for. And this epsilon could also just be noise, or it could be some non-linear true relationship in our data that the linear model is not able to capture, of course, because it is a linear model, not non-linear model. Talking about these residuals, which are nothing else but the difference between the reality and the predictions of our linear model, they must meet certain requirements that the linear model asks. For example, they have to be independent and identically distributed. So if we were to look at a scatter plot of these residual terms, we should not see any kind of structure in those residuals. And then they are also asked to be normally distributed with a mean of 0. So their values should vary around 0 and they should follow a normal distribution. So I will show you a bit later how these residuals should look like, ideally, if we were to build a very, very reliable linear model. So now my suggestion is to start with just a very simple example of predicting the price in euros based on the size of the apartment. We could look at the correlation between these two variables by using the Seaborn scatter plot, and we are just going to pass in the data, and on the x-axis we will plot our size of the apartment. So we are just going to create exactly the same plot that I've explained you on, but now with our data set. And then on the y-axis, we are just putting the price in euros. Okay, just go up here. Okay, so this is how our two variables look like in relationship to one another. So this was also visible, this correlation was also visible in the pairs plot. Now, what Seaborn has, and it's a really useful plot, is the LM plot, which plots a linear model. So basically what we are trying to build. And what this does, it just estimates a linear equation that is going to describe our scatter plot. And we can see that this is such a linear model. Okay, so the parameters are not known to us. We don't know which is our intercept, that is the alpha, where the line intersects the y-axis. And neither do we know which is the slope, like as a number. But that's fine. We are going to find these values when we are training our model. So the setup is going to be the following. We are going to initialize the linear model by passing in the arguments. The y is going to be the data price in euros, and our x is going to be the data size. So now that we've initialized our model, the next step is to train it, or to fit the model. And I'm just going to call it LM. This is all it takes. Okay. Okay, no worries. Then I'm just going to delete. Probably it doesn't have. Okay, so this is everything it takes for a linear model to be fit. Now we are going to look at its output and we are going to try to interpret it. And I've chosen to use the stats models package because it outputs a summary very similar to the R summary. So for those of you who are already familiar with R and know how to interpret all these numbers, then probably you won't have to bear with me here. But then for all of you who are just starting off with data science, I think the next step is going to be interesting. So the dependent variable, or what we are trying to explain, is the price in euros, and we are doing it by using the ordinary least squares method, and we are doing this on 161 observations. So we have 161 samples. Now the degrees of freedom of the residuals are 160, and this number is calculated by subtracting from the number of observations the number of predictors that we are using in our model, and the intercept also counts towards these degrees of freedom. So if we, for example, fitted a model which apart from the size would also include an intercept or an alpha parameter, then we would have 159 degrees of freedom. R squared and R squared adjusted are measures of how well our model fits the data. Their values range between 0 and 1, with 1 being the ideal situation, the maximum value that we can reach. And what this would mean is that the predictors that we included in our model are able to capture the behavior of the dependent variable perfectly. So there is nothing else that we could add to the model that would add value to our predictions. The difference between the adjusted and non-adjusted variant is that the adjusted R squared penalizes for the number of predictors that we include in the model. So it penalizes for the model complexity. The F statistic measures the existence of a linear relationship between our dependent variable, price in euros, and all the predictors that we've included in the model. And it also takes into account the number of samples that we are training the model on. So if we have a very large sample size, for example, tens of thousands of samples, and an F statistic which is above 1, but just slightly above 1, that could be already an indicator of a linear relationship. But with a smaller sample size, the F statistics would have to be really high. So we see that it is here over 2000. So this probability of the F statistic is more relevant because the lower it is, more of a linear relationship it indicates. Then we have the log likelihood, the AIC and BIC, which are the Akaike information criterion and the Bayes information criterion. So these are metrics that we are going to monitor when we are performing variable selection, because they penalize for the complexity of the model as well. The BIC penalizes more than the AIC, actually. The next table gives us information on whether the predictors that we chose to explain the behavior of our dependent variables are relevant or not. And the measure that indicates that the predictor is significant is this p-value. Setting a confidence interval in our situation of 95% would require that our p-value is below 0.05 or below 5%. If that is the case, then it means that our predictor is relevant or is significant. Now, how do we reach this conclusion? So we have here the coefficient, which is nothing else than our beta that we tried to estimate. So this is the intercept. Then we have the standard error of this coefficient, and by dividing the value of the coefficient to the standard error, we get a t-statistic. This t-statistic is what is going to help us assess whether the predictor is relevant or not. How? Well, t-statistics follow a t-distribution, which is an approximation of a normal distribution. And we know that in the tails of the distribution, we have the most extreme events that have the lowest probability of happening. So then also in the tails of a t-distribution, we will have extreme events. Now, the thing is, how do you formulate the null hypothesis? The null hypothesis is that such a t-value is the result of some data generated from a random process. Then you are going to look at what are the chances that you get this value of the t-statistic given that your data is generated from this random process. And if that probability is small, then you are going to reject the null hypothesis. So that's why you are looking for probabilities which are lower than 5%. Because what you actually want to do here, in order to conclude, yes, my predictor is relevant, it's significant, is reject the null hypothesis. You want to prove that this predictor is actually capturing some underlying pattern in your price, in your dependent variable, and it is not just some result of a random process. Please allow me to give you a visual intuition into how the p-values and the t-statistics are connected with one another. There is this website which offers a tool that you can use for free, Statulator, and here on the right hand side we have a t-distribution, which, as you can see, is very similar to a normal distribution. The difference lies in the fact that in the t-distribution, the variance is estimated through the degrees of freedom. So our data set has 160 degrees of freedom, and we are going to choose that. And we have a confidence interval of 95%. So what we want to do now is insert here the t-statistic value that we obtained with our regression, and that is 53.041. And now we are going to visualize where in this distribution our value, our t-statistic, lies. Does it lie in the tails of the distribution or in the center of the distribution? If we click Visualize p-values, we get the distribution corresponding to our 160 degrees of freedom. What this graph tells us is that the t-statistic value of 53 that we obtained with our coefficient lies in the tails of the distribution, very far away from the mean. And the probability of this t-statistic is very low. It is actually 0%, which is also the p-value recorded in our table. Suppose that for the same degrees of freedom, our t-value were, for example, 2. So if our t-statistic were 2 on the same data set, instead of 53, would this still indicate that our coefficient is significant? According to this distribution, yes, because the p-value, or the probability of having a value of these statistics equal to 2 is under 5%. So keeping in mind that the size is going to be a significant predictor for the price of an apartment, our coefficient of 2764 would indicate that increasing the size of the apartment by 1 square meter is going to determine an increase in the apartment price by 2,764 euros. If the sign of the coefficient were negative, then the relationship would be inverse. So an increase in the size of the apartment would determine a decrease in the price of the apartment. Next table is about the residuals. So the distribution of the residuals seems to be skewed, and the kurtosis indicates the fatness of the tails. So what are the chances that extreme events will happen? So in conclusion, from this output, we can see that indeed the size of the apartment is a very relevant predictor for the price in euros of an apartment, and it explains a very high proportion of the variance in the price, around 94%, which is really high. So now we want to see, like, how can we evaluate this model's performance? So in order to do that, first we are going to calculate the predicted price by running our model, linear model, I think I called it, and predict with it. We are going to predict on the size of the apartment. Okay, so these are our predicted prices. Now, if we were to compare the reality, which is the true price, and the predicted prices, we would get the residuals. In order to do that, I'm going to calculate the residuals as the difference between the price in euros and the predicted prices. Okay, so these are going to be our residuals. Each metric that we are going to employ today is going to compare these two things, the true price of the apartment and the predicted price of the apartment. The first metric is the mean absolute error. This is going to be between the true price and the predicted price. The mean absolute error is 29,000 euros. This means that our model is going to make mistakes on average of 29,000 euros. So it might predict lower than that or higher than that, but on average, this is the mistake that it will make. Then we can also look at the mean squared error, where we square each one of the residuals and then we calculate the mean on all these squared residuals, and then we pass in exactly the same parameters. So now we see that this value is actually much larger, because instead of simply calculating the mean of the simple residuals, we are first squaring our residuals and then calculating the mean on those. But from this metric, we can also calculate another metric that is also expressed in the same unit, so also expressed in euros. That is the RMSE from root mean squared error, and this is going to be calculated as the square root of, let me call this mean squared error, and this I'll call mean absolute error. So this is just the square root of the mean squared error, and now I'm just going to print my mean absolute error and print the root mean squared error. Okay, and we see that the root mean squared error is 39,000 euros. So in my opinion, if I were to buy an apartment, having a model that predicts the price of the apartment like with 39,000 euros more than the actual price would be bothersome. So I really do not consider that these values are very good predictions. So let's inspect the residuals and see exactly what happens there, because as I said, there are some assumptions that residuals must respect in order for a linear model to be reliable. One is the normality of the residuals and an average of 0, and then the other one is being independently and identically distributed. For this purpose, let me show you how should these assumptions look like if they were respected. So in this plot on the left, we can see the assumption of independently distributed and identically distributed. So we do not see any pattern in the scatter plot. And then on the right hand side, we see what does it mean that the residuals are normally distributed. Now let's look at how our residuals are distributed, and then just assess if they are normally or not. I'm going to do this. So this is how the scatter plot of our residuals look like. It doesn't seem to be independent or identically distributed. Moreover, it also exhibits some outliers. Also on the left hand side as well as on the right hand side, and these are also visible in the histogram. One plot that is usually employed in analyzing the distribution of the residuals is the QQ plot. We are going to generate the QQ plot with the prob plot. We are going to pass in our residuals. Then we are going to test for normality. And we are going to use a PyLab style plot, and just with plot show our residuals, of course. Just going to say dist norm. Okay. I can see from this plot that I have some outliers, and this is indicated by these really heavy tails on each side of the distribution. So one thing that I could do if I continued to move forward with this simple model is remove the outliers. But what I would rather do is add some additional variables to my model or increase its complexity, and then see what happens then. So what I would like to add as a predictor, besides the size of the apartment, is the year that the building was built in. And then I would also add, for example, the number of bathrooms and see what happens now. I can see actually that all of the three predictors are now relevant. No, the year built is not relevant because the p-value is larger than 0.05. It is 0.07. But the size and the number of bathrooms are both relevant predictors. Let's see if the model performance is improving. So from a root mean squared error of 39,700, I'm going down to 38,000, which is very slight improvement. And now I want to check how my residuals are distributed. I see that they are still around the value of 0, but outliers are visible also with this improved or more complex model. Inspecting the QQ plot indicates that indeed I still have some residual values. What I would like to also look at is how far away from the reality my model predicts. So in order to do that, I'm going to add this new column, which is the predicted price, to my data frame. And then I'm going to plot a scatter plot with Seaborn of the true values versus the predicted values. So first I'm adding my new column, which is predicted price. I'm going to also display the ideal line, so which would be the scenario if my model predicted exactly the reality or perfectly. So I'm just going to plot the price in euros against the price in euros and then just color it in a different color. Okay, so I hope that's going to work. Yes. So as I can see here, my model, or like the orange dots, would be the ideal case when my model would predict exactly the reality. The predicted price is here on the y-axis, whereas the true price in euros is on the x-axis. So two things pop up. One is that when the true price of the flat is here on the lower spectrum, my model has a tendency to predict a higher price, whereas for those flats that are really expensive in reality, my model is predicting lower prices. So basically, these indicate the outliers that I saw in the QQ plot. It might be actually that there is some nonlinearity in the data that the model, the linear regression, cannot capture adequately. What I could do is just try to see what are these points' characteristics. Is it something that I could learn from? So what I could do is just explore the number of rooms each of these apartments has, and then just draw the size of these points according to the size of the rooms. Okay. Then here I have my legend, and I can see that oh sorry, not the size of the rooms, but the number of the rooms. I see that all those apartments that are with one room only appear here at the bottom of the scatter plot in the bottom left corner. And then here what I have are apartments which are larger in terms of the number of rooms they have. Okay, but this still doesn't give me much information. Okay, maybe it is about the year that the apartments were built in. So let's check the year built. Okay, so it seems that these very high prices are related to some apartments that were built not far from now, the ones that were built in 2024 or 2016. So it might be that amid the increase in the prices of construction materials, the prices of the apartments have also increased. What I would like to do next is check if adding the number of rooms to the model would make any difference. I'm adding the number of rooms because although the size of the apartment and the number of rooms in the apartment are to some extent correlated, actually it might be the case that adding this variable would add additional information to the model. This happens because there are, for example, like 30 square meters apartments that only have one room or two rooms. So maybe we could differentiate the price a little bit better based on the number of rooms and the size. And I'm going to run the linear model again. And now what I can see is actually that the number of rooms is not a significant parameter. And the year the apartment was built, the building was built in, becomes even more insignificant. I'm going to exclude this variable again. So I'm going to go back to the model that I've previously had. And now what I'm going to try to leverage on is eliminating some of the outlier values. I have the impression that these very extreme points are affecting the predictive model. I'm going to find all these data points which have value below maybe 50,000, or let's check here. First of all, I'm going to exclude this outlier here because we have a very clear gap in the histogram. So this is an outlier for sure. And then from here, from the positive side on the right tail, I'm going to exclude from the first gap onwards. So those would be values maybe around above 80,000. Okay. So now what I have to do is just identify the position in the data frame of these points which are constituting outliers. And to find the position in the data frame, I'm just going to use the residuals and identify those residuals which have a value lower than 50,000, minus 50,000, negative, sorry. Okay. Okay, so maybe I don't want to exclude all of these, so I'll just say, to be safe, minus 70,000. Okay, so I have only this 1 point. And then I'll also need the positive values, which are above, let's say 70,000 positive, no, 90,000. Okay, and now these are these other values. I only want to extract the indices, so I'll just limit myself to extracting the indices, and that's the positions, and these are going to be my negative outliers, and these are going to be the positive outliers. And I'm going to convert it to sets. Okay, and now what I'm going to do next is eliminate the rows from these positions from my data. And I'm going to convert it to a list instead of a set, and I'm printing its length. So now I have 152 rows instead of having 161. Okay, so then my data is just going to be overwritten by this by the dataset that only contains the rows that are not outliers. And I can do it like this. Now I want to check that the length of my data is also 152. That is true. And the next step is to rerun the model. So let's see how our model behaves now that we've eliminated the outliers. So I still have two variables that seem to be relevant. And let's see if our root mean squared error decreased. Yes, it decreased with by 10,000 euros, which is very big decrease in terms of how accurate we are predicting. If we inspect the residuals, we see that we still have some outliers here on the positive side, which we could eliminate in order to get even better predictions than these. And the QQ plot confirms that yes, we still have some outliers. But now let's see how far away are our predictions from the true line. And we can see that they look better. The line seems to better capture the effects now that we've eliminated the outliers, like the problematic points. So normally you would have to eliminate the outliers one by one and then see what happens, because it might be the case that excluding only one outlier from the negative zone, for example, would align the line such that it better captures the dynamic of the data. What I would like to try and do next is maybe just standardize the variables, because they come in different units, right? So the year is in the thousands, the size is in the tens, and the bathrooms ranges from 1 to 3 or to 4. So it might be the case that, for example, one variable eclipses the other variables here. So size, bathrooms, and year built. So I'd like to see if this positively impacts my model or not. and if not, then that's just fine. I would say no, it does not. The first thing to look at is the R-squared or the R-squared adjusted, which are becoming so low. So basically, when we are actually normalizing the values without adding an intercept, we are not able to capture the prices of the apartments very well. I'm curious to see what would happen if I added an intercept. If I added a constant, okay, that makes a very big difference. So a constant would make a really big difference because the R-squared adjusted just jumps to 75%, which means that with an intercept and my three variables, which all of the sudden become so relevant, like they are all significant, I'm able to capture 75% of the variability in my price of apartments. So let's see if by adding an intercept and standardizing the variables, we are able to reduce the root mean squared error. And yes, we do. So now the root mean squared error is 28,000 euros. Okay, so let's see now how our errors are distributed. They seem to be more normally distributed. Again, we have these outliers here, which I would say we could also exclude. But probably by now you are going to ask, when is this tutorial going to end? So I promise that the last thing that I'm going to do is exclude these outliers and then just check again if the model would better predict or more reliably predict. And what I'll do is just exclude everything that has a residual value above 60,000. And now I'm just going to exclude those data. So now I only have 144 observations instead of what I had before, which is 152. And I am going to run this again. The R-squared and the adjusted R-squared increased, which is really good. All my variables are still significant, very significant, which is again very good. The kurtosis on my residual distribution decreased, so this means that my tails are not as heavy as before. And also the skewness, so of course, because I removed points from it, just to try to meet the assumptions of a linear model. And now I'm calculating the residuals again, and I want to see if my root mean squared error is going down from 28,000 to 23,400, which is again an improvement in the model. So this is actually how things are going when you are trying to fit a model in real life. You will have to go through multiple iterations and try so multiple things. Now it looks like my residual distribution doesn't follow a normal distribution. But as I removed data points from my dataset, I might just have to adapt the number of bins that I'm using. And when I lower the number of bins, because now I have a lower number of data points, so it looks like 20 bins would actually indicate sort of a normality of the distribution. And I can see also that the residuals do not really exhibit any type of pattern, so they are meeting also the assumption of being independent and identically distributed. When inspecting the QQ plot again, I see that all my points almost lie on this straight line, so this is much better than what we've started with. And this is what we want to have. Of course, we are allowing for some outliers, for some limit cases, but we really need to make sure that we are meeting the assumptions of the linear regression. And also here, when I look at like how my ideal predictions would be, I can see actually that the dispersion of the points is lower and that my predictions lie closer to my ideal line. So this is also a good sign and an indication that this model that I've trained is going to predict more accurately. So which is the best model and with which should we go on forward? If we were to put it, for example, in a production pipeline, from what we've tried today, I would say that the last model is the best, and the justification is that even if the R-squared adjusted is lower, around 85%, compared to when we only used one predictor, which was the size of the apartment, and when we had an R-squared adjusted of around 97%, the performance metrics of the model, namely the root mean squared error and the mean absolute error, are lower when using multiple parameters. We also used normalization or standardization. In a real-life scenario, what I would do next after exploring the linear regression algorithm is look at other algorithms able to capture nonlinearities in the data. If you've found this tutorial useful and you would like to learn more about applied data science from similar tutorials, then don't forget to subscribe to my channel and never miss anything that I post. Have fun with data science and see you next time.